Okay, hello, welcome back. This is 3.7 related rates, and seems like I'm dealing with a bit of a cold, so just hang in there with me. Anyways, for solving these related rate problems, it's pretty simple. What you do is kind of fabricate an equation and two variables. So you basically write an equation. So it's going to be, these are going to be story problems, okay? In the beginning problems, they give you the equation, but in general, you'll have to make the equation, which relates to, or even sometimes three unknowns, okay? Secondly, you're going to differentiate everything implicitly. Okay? So you pretend all of the variables are kind of functions of some third variable that you're differentiating with respect to. Okay, so you'll see what that means here in a bit. So once you differentiate implicitly, you're going to have all these kind of derivatives floating about, and that will be the related rates formula. Okay, and we will, in the third step, sub in information to solve for unknowns. Okay, it's pretty simple. Sometimes the first step can be kind of challenging, as you'll see in some of these exercises. So let me go to the book and see what exactly is going on there. So these first couple problems, like I said, you're basically just plugging in. They give you the information, and then you're going to plug in the stuff. So let's look at number three, I guess. So they give you the equation, right? So y equals the square root of x. I'll just do part A. So this is given information. They want you to find dy dt, and they're telling you that x is equal to 4, and dx with respect to dt is equal to 3. Okay, so you're differentiating implicitly, but you're going to treat everything as though it was like you're differentiating y, right? Because you're always going to be tacking on a y prime. Even for the x, you're tacking on an x prime. And in this context, the variable you're taking the derivative with respect to is this third variable t for time. Okay, so here we go. Let me rewrite it with a fractional exponent, and then we're going to take the derivative. Okay, so the derivative of y is just 1, but then you have to tack on the y prime. Instead of writing y prime, we're going to write the Leibniz notation version, dy over dt. Okay. On the other side, then, the derivative of x to the 1/2 is 1/2 x to the negative 1/2, and then we have to tack on the derivative of x with respect to t, times the derivative of x with respect to t. Okay, and then we can clean it up a bit. And to find dy over dt, we just plug in the given information right here into here. And we'll find that dy over dt is equal to 1 all over 2 times the square root of 4, which will be 2, times dx over dt, which is given as 3. So our answer, 3/4. Okay, so pretty easy. Let's do number 5 and see how that goes. So we have xy equals 4, and we'll do part A. They want you to find dy over dt when x is 8 and dx over dt is 10. So if they wanted you to find dx over dt, you would just have to solve for that. Okay, so anyways, let's look at this. You're going to have to do a product rule, right? So leave x alone, and then the derivative of y is 1 times y prime, or dy over dt now. I'll write it that way. plus the derivative of x is 1 times dx over dt. Okay, times y, leave y alone. And on the right-hand side, the derivative of 4 is 0. Okay, so we'll have x times dy over dt. We want to solve for dy over dt. And we have dx over dt times y, put the y in front, equals 0. So I'm going to solve for dy over dt. So first subtract the y times dx over dt. Oh, I forgot my y. There it is. Then divide both sides by x, and we get a formula for dy over dt is negative y all over x times dx over dt. Okay. So then we just sub in our info. And there's one extra tidbit here. Of course, we don't have y, but we need a y. So what we'll do there is just go back to the equation and figure that out, right? So if x times y is 4, then y must be equal to 4 divided by x. And our x is 8, so y must be equal to 4 over 8, which is 1/2. Okay, so we're plugging all that material into this formula, so I have negative 1/2 all over x, which is 8, and then times dx over dt, which is 10. I have to simplify all this material. 1/2 divided by 8 is the same as 1/2 times 1/8, which is negative 1/16, times 10. So it looks like we're getting negative 5/8 for our rate. Okay, so those are the easy ones. Now we want to head more towards the application type problems. So first kind of application, we pretend that the equation represents a point moving in the plane. And then we want to solve for whatever rate. I guess they want you to find the rate of change in the y direction for given values of x. Okay, so let's try number 7, I suppose. Y equals 2x squared plus 1. And they're telling us dx over dt is equal to 2 centimeters per second. And I'll just do part A. Okay. So they want to know the rate of change of in the y direction when x is equal to -1, and the rate of change of x is 2 centimeters per second. Okay. So again, they've given you the equation. All you're going to have to do is differentiate implicitly. So the derivative of y is 1 times dy over dt. On the right-hand side, the derivative of 2x squared will be 4x times the derivative of x with respect to dt. With respect to t, the derivative of 1 is 0. And then we could just plop in our information. Okay? So we have 4 times -1 times 2, which will give us -8 centimeters per second. Okay? So again, pretty simple so far. Let's see. Okay, so now we get more complicated with the area problems. So this first one, let's try number 11. The radius of a circle, r, is increasing at a rate of 4 centimeters per minute. Find the rate of change of the area when r is 37 centimeters. Okay, so I need an equation that relates area and radius. And of course, we know the formula for the area of a circle is A equals pi r squared. Okay, so we got that. We need to differentiate this thing implicitly in order to work with it. We'll have the derivative of a with respect to t equals, on this other side, bring down the 2 pi r to the first power times the rate of change of r with respect to t. Okay. I should have wrote down the given information, but what do we have? The rate of change of the radius, which is dr with respect to dt, is 4 centimeters per minute. That's given in the question. They want you to find the rate of change of the area when r is equal to 37 centimeters. Okay, so it seems like all we have to do is plug that information, this given information, into our formula right here. Okay, so let's try it. dA over dt is equal to 2 pi times r, which is 37, times dr with respect to dt, that's 4. Okay, and then I probably need a calculator to figure that out. I would like to blow my nose, but there's no tissue. Magically, my tissue box has disappeared. So I will just have to hold that in. 2 times 37 times 4, 296. Okay, so this will be 296 pi, and the units, because we're dealing with area, must be centimeters squared. Okay, centimeters squared per minute. Okay, let's look at another one. Volume of I guess a sphere. So the radius r of a sphere is increasing at a rate of 3 inches per minute. This will be number 13. So they're saying the rate of change of r with respect to time is 3 inches. I'm going to get my given information first this time. 3 inches per minute. Find the rate of change of the volume when r is 9 and then when r is 36. Okay, so when r is 9 and then again when r is 36. And these are inches. Okay, so I need an equation that relates everything. These equations are kind of, hopefully you could just Google them if you need one. If I have a test, and I think our test this time will be on my math lab though, or WebAssign, sorry. So how would you get that equation if you didn't know it? Well, I'll make sure you have the equation if you don't know it. You can. Don't worry. But anyways, the volume of a sphere is 4/3 pi r cubed, if you did not know. And so now we need to differentiate that implicitly. We're looking for the rate of change of the volume, so dV with respect to t. So go ahead and take the derivative of this implicitly with respect to t. The other side here we have bring down the 3 times the 4/3 pi times the r now to the second power. Okay, so the rate of change of volume with respect to t will be 4 pi r squared. And then we want to put in our given information from above. So when r is 9, the rate of change of the volume with respect to time will be 4 times pi times 36. Okay. 4 times pi times 36. So, and then we need the 3 as well. So 4 times pi times the r squared, which is, sorry, not 36, but that's 81. And then times 3. Okay, and then I'm going to have to go to my calculator for that one. 4 times 81 times 3, 972 pi. Okay, so 972 pi, and volume is cube units, so it'll be inches cubed per minute. And then when r is even bigger, apparently, we want to go with 36. The rate of change of the volume with respect to time will be 4 pi times 36 squared, whatever that is, times 3. And what do we have? 36 squared times 4 times 3 is 15552 pi inches cubed per minute. Okay, great. Part B, explain why the rate of change of the volume of the sphere is not constant, even though the rate of change of the radius is constant. Well, you can just look at the formula. It's dependent on radius squared. Okay, so, and you think about it visually, when you have a bigger sphere, when the radius is bigger, and the radius then increases on top of that, the volume that's being swept out will be much greater. So you think of a small sphere expanding, and it's not going to be a lot of volume compared to a bigger sphere expanding that same amount. So something along those lines. I guess that was supposed to be some sort of penetrating question. I don't know. Okay, so let's go on. Number 19 is always kind of a headache. So let's take a look at that guy. A swimming pool is 12 meters long. They give you this big ugly picture here to the right. 1 meter deep at the shallow end. Water's being pumped into it. So what that means is there's a rate of change in volume of 1/4 cubic meters per minute, and there's officially 1 meter of water in the deep end. What percent of the pool is filled? Okay, so you need 2 things for part A. You need the volume of the pool, and then the volume of the water. Let's get the volume of the pool first. Okay, so you know, whether you can see it or not, there's 2 sections of this pool going about. There's kind of this upper section, which is a rectangular solid of sorts. Okay, so we need to find the volume of that part of it. And then there's this lower section. I'm drawing the top yet. There's this lower section, which is kind of a triangular type deal. It looks like this, and then it's getting hooked up there. Okay, and then there's some water in it. I can actually do some other colors here. There's some water down in here. Okay. So the dimensions here then, we have this is 1 meter. This dimension I think is 6 meters. This is 12. Okay. And this is 3. And this is 2. And then the amount of water in the pool at this time is 1. This is all given information, in case you're wondering where I'm getting at. It's on the, you can see it to the right there. Okay, what else? Is that about it? Okay, so the volume of the pool, there's 2 parts, right? There's that rectangular solid part, and the volume of that is just length times width times height. So 6 times 1 times 12. And then there's this other triangular bit, this kind of wedgy thing, and then you get the area of that. You just take the area of the triangle and multiply it by the depth of the thing. So you need the area of this triangle in the front here, and then you just multiply the area of that triangle by 6, and that'll give the area of that triangular wedge. Okay. Okay, so the area of that triangle, 1/2 base is 12 times its height, in this case is 2, and 1/2 base times height, and then times that 6, this depth. It's kind of like the formula for a cylinder. 1/2. What's the formula for a cylinder? So it's the base pi r squared times the height of the can, right? H. See, a little elementary geometry, I guess, to pull that off. But anyways, if you figure that out, it's going to be 72 plus 72, which is 144 meters cubed. Then the volume of the water is a little more work. In particular, you're going to have to use similar triangles now. Okay, so you kind of have this situation going on with the water. So we can look at, maybe if I draw it in red, I want to look face on at this part of it, and then use similar triangles to figure out the volume of the water. Okay, so that red part that I just kind of drew in, looks like this, and then there's the water going through it right here. So I need the area of the water portion right here, and then multiply it by 6, and that'll give me the volume of the water. Okay. But in order to pull that off, I need to use similar triangles. So I know that this distance is 2. I know that this distance is, I think, given as 1 in the book. The depth of the water at time whatever is 1 times 0, I guess. And then I know this dimension is 12. And then there's one dimension I don't know, which I'll just call x. Okay, this dimension right here. So I need that for the base of the triangle, 1/2 base times height. Okay, but I can use similar triangles. So I'll say 2 is to 12 as 1 is to x, and then just solve for x. Right. So I guess cross multiplying or whatever, get 2x is 12, and then x is 6. Okay. So the volume of the water, 1/2 base is 6 times height, and then times this depth of 6. 36 divided by 2 is 18 meters cubed. And then to finally find the percentage of water in the pool, you just take VW divided by VP and then multiply it by 100%. Okay? And if you do that, you'll get 18 over, I think it was 144 times 100%. And I did that earlier. It's 12.5%. Okay. So it's 144 and 18, yeah. Okay, part B, now they want you to kind of do a related rates type thing. At what rate is the water level rising? So I need a formula for the amount of water in the pool at any given time so it's a volume formula. And I'm going to be using similar triangles again. The trouble now is there's kind of like 2 unknowns. Okay, so I need a formula for the volume of water in the pool. I know that the rate of change of the volume of the water in the pool is 1/4 cubic meters per minute. That was given. Okay, so let's try that. I need a formula for the volume. Okay, so again, I'm going to use similar triangles to pull this off. And then there's water in there. So I know this dimension is 2. Okay? And then this dimension here was 12. Okay? And then I'm going to call this dimension x and this dimension y. So as it sits, the volume of the water in the pool will always be, if you use these variables here, x times y times 6, 6xy. But we want it in terms of just 2 variables. So we want to eliminate the x variable and just have it in terms of depth. Okay, because really, ultimately, I guess it's maybe not even the change in volume we're after, it's the change in depth. Okay. What is the rate of the water level rising? If you read the question part B, at what rate is the water level rising? So it's really the y, the change in y with respect to time that we're after. I do know the rate of change of volume. So if I can do related rates with y and v, then I'm going to be able to answer my question. Okay. So anyways, we're going to have to do similar triangles again to get a formula for x in terms of y. So 2 is to 12 as y is to x. And then I'm going to solve for x. Okay? So x will equal 6y at the end of the day, if you do cross multiply and solve. And then I could do a substitution into this formula. So I'll end up with volume is 6 times y, in other words 6y squared. And then you could differentiate implicitly. Okay, so you get dv with respect to dt equals 12y times y prime, dy over dt. Okay? And then I can go ahead and start filling in the blanks. In particular, they want to know at what rate is the water level rising at this point in time. Maybe they should have specified that. So when y is equal to 1. So again, our dv with respect to dt is 1/4, and our y value is equal to 1. That's the given information. We just substitute that in. So 1/4 equals 12 times 1 times dy over dt, and then we can solve for dy over dt. So dy over dt is 1 all over, this should be y squared, right? No, we took the derivative. So I'm thinking I screwed something up somewhere. It's 6 times 6 times y, sorry. So this should be 36 back here. And then this will be, sorry. This will be 72. Yeah, this problem is a nightmare, let me tell you. So wait, 72. No, it's 6y, and then I'm looking at my notes, and my notes, they're either wrong or I'm wrong, but I've done it so many times. Oh my gosh. Oh, the stupid formula is wrong for volume. All right, sorry. Oh my gosh, sorry. The formula for volume should be 1/2 base, which is x, times height, which is y, times the depth, which is 3 or 6. So this will be 3 times x times y. Then we do our substitution, so that'll be 3 times 6y times y, which is 18y squared. And then we can do our derivatives, which is 36y times dy over dt. Then we can do our substitutions and solve out for dy over dt if you wish. So this will be 1/4 equals 36 times 1 times dy over dt, and then dy over dt will be 1 over 144. What is that? What are the units? Meters per minute. Okay, sorry about that. Okay, let's go on to the next problem. The next one is on kind of air traffic controlling, so 25. We have two planes kind of zipping towards each other. We want to know the rate at which the distance between the planes is decreasing. So 100, 200, 300. We have one plane at 300 miles out. Okay, so 0, 300. Going towards the origin at a rate of 600 miles per hour. And then we have another plane that's 225 miles out, moving towards the origin at a rate of 450 miles per hour. Okay, so just looking at the rate, if this thing's 300 miles out and it's moving 600 miles per hour, in 1/2 hour it'll hit the origin. And same for the other guy. If it's 225 miles out and it's moving 450 miles per hour, it will take half an hour to get to the origin. So they're going to hit in a half hour. We want to know the rate of change of the distance between the two. Okay, so that length that I'm calling cursive letter S. Okay. So part A, let me find where I am in the book here. It's this problem. Part A, at what rate is the distance S between the planes decreasing? So we need to do a related rates type thing. There's an x, there's a y, and then there's a s. So Pythagorean theorem says that s squared is equal to x squared plus y squared. then you could differentiate implicitly. So we have 2s ds with respect to dt equals 2x dx with respect to dt plus 2y dy with respect to dt. We can simplify this a bit by dividing by 2 and then divide by s, and that'll give us a nice formula for ds over dt. So you end up being x dx over dt plus y dy over dt all over s, which is equal to, if you use this formula, the square root of x squared plus y squared. Okay, so I get a nice formula for the rate of change of the distance between the two planes, completely in terms of x and y. Right? So the given information is telling me that the one plane, we want to know the rate of change of the distance between the planes when the one plane is 225 miles out and its rate of change is what did we say, 450 miles per hour. And you may want to put negative 450 just to indicate it's going towards the origin as opposed to away, but I don't think it'll matter. Then the other plane is initially 300 miles out and its rate of change was 600, so I'll put negative 600. And then finally the s value, or in other words, the square root of x squared plus y squared would be 225 squared plus 300 squared, which will equal 375. And you just plug all of this information then into this formula here, and that'll give you the rate of change of the distance between the planes. Okay, so if you do that, you're going to end up with a whole bunch of numbers. 225 times negative 450 plus 300 times negative 600 divided by 375, and then ultimately will equal negative 750 miles per hour. So very, very quick. The rate, it's almost, almost twice as fast as the rate of the x plane, the plane on the x distance. So. Okay. How much time does the air traffic? Well, a half hour. We already said at the beginning it's going to take a half hour before they hit each other. This is actually related to a real-world situation. This, if you're very sensitive to airplane crashes or anything, you may want to fast forward through this part of the video. It can be very upsetting. But I'll go ahead and start it now. So if you want to maybe mute, you don't want to hear this, it's kind of grisly, relatively grisly, but you may want to mute the video as we go into this part. Okay, so I'm going to start the grisly part right now. In particular, here's an F4. I just went to the Air Force Museum over the weekend. Back in the day, the air traffic controllers and the military air traffic controllers, like civilian and military, they didn't really communicate very well to each other. Some other planes from my travel to it's in Dayton, Ohio, and I just had a student graduate from Dayton. He was really into airplanes and stuff. There's me in front of a V-2 missile, which is a World War II missile, and all kinds of technological developments and that sort of thing. Okay, so if you ever get a chance, go down there and check it out. Sinclair Community College is also down there, which is another good community college. But in particular, we're worried about the F-4, which was in use in the Vietnam War. And again, one of the issues was that civilian and military aircraft controls didn't really communicate to each other. And another issue was the relative rates at which the airplanes were descending on each other, and that rate at which the distance between the two planes was going down. Okay, so this is the Ntsb report, which is not over your head. Okay, you can go and read these things, and you have the math skills to handle this report. Okay, so let me sort of zoom down to the more important bits. So what happened is an F4 collided with I think it was a DC-10 or DC-11 or something like that, a DC-9, sorry, and you know, both planes crashed. I think everybody on board the DC-9 was killed, and the F4, one of the pilots survived. Okay, so one of the issues was that rate at which the two planes were headed towards each other, and it has to do. The problem is the cockpit view. If you look at like the here's some of the cockpit views for the F4 and the DC-10. This is a DC-9 cockpit view. See if they give you the F4 cockpit view somewhere. Yeah, here's the F4 cockpit view, and you can see the F4 in my picture here. So the problem is they're coming at each other so quickly that initially for the F4, the DC-9 would just be a dot, and the dot could actually be in between the window panes, right? So initially the plane could be in this little wedge here, and it's going so fast. So you see over here, it's going, maybe it was right here, it's just a dot and the pilot can't see it, but it's going so fast it ends up in here. And then by the time it's over here, I mean, you're hitting it basically. So that's kind of the issue with the relative rates. And this picture right here is exactly what we were just doing, except in our problem, we had to do, we had a Pythagorean identity we could use because we're dealing with a 90-degree triangle. And this one, you would have to use one of the, I forget the cosine formulas, like a squared equals b squared plus c squared minus 2 a squared cosine theta or something. You have to use that formula and then implicitly differentiate it, and you could work with it. Okay, a couple of years ago I did go through it and just to verify all of their math, and you could see they gone through and found the rate of change for every particular moment that they were worried about. But this is well within your guys' ability to work with if you wanted to go in there and read about it. I just went and Googled basically DC-9. I Googled F4 collision NTSB Phantom jet collision, and then I went to here. So it's a Hughes Air West Flight 706 Wikipedia page, and then I went to the Ntsb report, which is right here, I believe. And then that gave me the Ntsb report, and I can go read it. Okay. It's a bit macabre, but the people do this, and it's very important work. Okay, so there's that. And it's related to everything we just did. You can apply the methods we just did. Okay, great. Let's get back now. I'm done with the Grizzly report, so done. Let's get back to work, okay? Okay, so done with the Ntsb. So hopefully you can go ahead and unmute if you need to. Unmute your video. And hopefully you're back with me. So we're going to try number 31, which is more of a mechanical application. So I've had a couple machinists in my classes over the years. Let me get rid of this and get back to the book. And this one is more along those lines, which may appeal more to you guys. And there's, I'm trying to get this thing to scroll down. Okay, get out of the way, please. Okay, so let's look at this one. It's some weird machine that's kind of, this thing is going back and forth. At the same time, this thing is going up. Okay, so this is a rigid rod right here, and it kind of forms a triangle, and we'll be using that. So there's one piston up here, okay, and then there's this rigid rod, and it connects to this other piston right down here. Okay, and then this is going back and forth. This point here is x 0, and this point up here is 0y. Okay, the position of the piston on the x-axis, so to speak, is given by formula. X of t equals 1/2 sine of pi t over 6. Okay, t is in seconds. And what do we want to do? So find the time for one complete cycle of the rod. So you could just easily find the period of this formula, and that'll do it. So for the period, you just take the insides of the sine and wedge it in between 0 and 2 pi, and then solve for t. Okay, so multiply through by 6 over pi, and you'll get 12. So one complete cycle in 12 seconds. What's the lowest point reached by the end of the rod on the y-axis? So you have to think about this in terms of the mechanism. So as this rod goes way to the right, all the way to the right, then this other, I guess, piston is going to achieve its lowest point. Okay, so if you can find where the thing, the X machine, is kind of at a maximum X value, then you've found where the Y, the time at least, where the Y will be at its minimum. And we could exploit a relationship between the X and the Y using, again, the Pythagorean theorem. X squared plus Y squared equals 1, okay, because the length of this part here is 1 meter. Okay, so somewhere I want to note that x squared plus y squared is equal to 1, and I want to find the maximum x value. So the maximum x value will happen when the angle inside of sine is pi over 2, because sine is maximum at pi over 2. If you think about the sine function as a graph, it looks like this, right? And it hits its max value at pi over 2. Okay, so we want a t value such that pi times t over 6 is equal to pi over 2. And you just solve that equation. So t will equal 3 if I multiply both sides by 6 over pi. You'll get t is 3 seconds. That'll allow you to solve out for the x value, which will just be clearly 1/2. Okay, so that's just the amplitude here. So you could have just said, oh, it's 1/2 automatically, because that's, I guess, you could have just done that. So the maximum x value is 1/2. So the minimum y value, then, if you look at the relationship between x and y, this will be y equals the square root of 1 minus x squared. And then we could just plug in 1/2 for x and get the corresponding y value. Okay, so this would be 1 minus 1/4, which is equal to 4/4 minus 1/4 is 3/4. If you take the square root of that, you get square root of 3 all over 2. Okay. Right. So part C then, find the speed of the y-axis endpoint when the x-axis endpoint is 1/4. So this is the related rates part. They want to know the rate of change of y with respect to t when x is equal to 1/4. Okay. Okay, so let's dive in there. We have our I guess our formula for x with respect to t. So let's think how this will work. X with respect to t. So we're going to have to kind of combine two formulas. It's almost like you have to implicitly differentiate two formulas. First, this x of t formula. And then also this other x squared plus y squared equals 1 formula. Okay. Okay, so right, let's do this one first. The derivative of x with respect to t then is equal to 1/2 times cosine of pi t over 6 times the derivative of pi t over 6, which is just pi over 6. So the rate of change of x with respect to t will be pi over 12 cosine of pi t over 6. Okay. Ultimately, what we want, there we go. There's more room here. So we're going to want to use that x squared plus y squared equals 1 formula to get a related rates problem. So how does this going to work? It's going to be 2x dx with respect to dt plus 2y dy with respect to dt equals 0. And then we could solve for dy with respect to dt. Divide everything by 2, then move the x dx with respect to dt, and then finally divide everything by y, and we'll have a nice formula for dy with respect to dt. The problem is we need basically 3 things for this formula. We need x. We have x. X is given as 1/4. We need dx with respect to dt. We don't know that. And we also need y. And we can get y from our x squared plus y squared equals 1 formula. So that's not a big deal. But the dx with respect to dt formula, that's kind of what we're going after right now. Okay, it's right here. We need dx with respect to dt. Okay, so in order to pull this off, I need to find the t value at which x is 1/4. Okay, so I'm going to use this formula now to solve that issue. So I have 1/4 equals 1/2 sine of pi t over 6. Excuse me. Multiply both sides by 2. I get 1/2 is sine of pi t over 6. And then I'm asking myself what angle such that I take the sine of would equal 1/2. Right? And then I can set pi t over 6 equal to that angle and solve. So sine of pi over 6 is equal to 1/2. So I set pi t over 6 equal to pi over 6 and solve for t. And of course, that's just going to give me that t equals 1. Okay, once I get t equals 1, I can go ahead and now find my dx with respect to dt. Right? So I take this formula, or rather this formula that's been simplified, and substitute in 1. Okay, so I'll get my dx with respect to dt equals pi over 12 times the cosine of pi over 6. Okay, and that'll equal pi over 12 times, I believe that's root 3 over 2. So root 3 pi, or if you'd rather, pi root 3 over 24. The only other thing I need then is the y value, and I can get y from this square root of 1 minus x squared, so 1 over 16. So that would be the square root of 15/16. In other words, the square root of 15 over 4. And then finally, I can plop all of that information into, let's circle the main formula in red. Sorry, this is a bit of a maze, I understand. It's probably hard to follow. I apologize. dy over dt, this is a hard problem, equals negative. So we want our x value is 1/4. And then our y value from below it is radical 15/4. And then dx over dt is pi radical 3 over 24. So simplifying a bit, 1/4 divided by radical 15/4 is the same as 1/4 times 4 over radical 15. So the 4's will cancel. I'll have pi radical 3 all over 24 radical 15. And we can simplify that a little bit, but and I lost my negative. My negative's there. I think I'll just leave it at that. Okay. Okay, let's leave it at that. That's a lot to stomach for one day. And thank you for watching, and we will see you next time.